Simplifying complex products and quotients using logarithms. Hello everyone. Let's begin today's session on simplifying complex products and quotients using logarithms. To start, let's look back at our foundation. In our previous lessons, we learned how to use the product rule and the quotient rule for differentiation. Now, while these rules are very effective for simple functions, you will find that they become algebraically cumbersome and tedious when you are faced with functions containing multiple products, several quotients, or a combination of various powers and roots. To solve this problem, we use a technique called logarithmic differentiation, which provides a much more streamlined and efficient alternative. The secret behind this method is that by applying the properties of logarithms, we can transform complex products or quotients into simple sums or differences of individual terms. Ultimately, this transformation simplifies the expression so much that the actual differentiation process becomes significantly easier. Over the next few slides, we will explore the specific mathematical properties that allow us to do this and walk through a step-by-step procedure to master this technique. The mathematical foundation, logarithmic properties. Now that we have established why the standard product and quotient rules can become cumbersome for complex functions, let us look at the tools we need to make the process more efficient. To master the technique of logarithmic differentiation, we must rely on three fundamental properties of natural logarithms. Please note that throughout this lesson, when we use the term log, we are specifically referring to the logarithm to the base e. First, we have the product rule of logarithms. This property states that the log of m times n is equal to the log of m plus the log of n in simple terms. This allows us to convert a multiplication problem into a much simpler addition problem. Second, we have the quotient rule of logarithms. This tells us that the log of m divided by n is equal to the log of m minus the log of n. This is incredibly useful because it transforms a division operation into a simple subtraction. Third, we have the power rule of logarithms. This rule states that the log of m raised to the power of n is equal to n times the log of m. This is a powerful tool that allows us to move exponents down in front of the logarithm as coefficients, effectively removing the complexity of powers. By utilizing these three properties, we can break apart a complicated function into a series of simple terms before we even attempt to find its derivative. Once we have simplified the expression using these rules, the actual differentiation becomes far more straightforward, which is the process we will detail in the next slide. The step-by-step procedure. Now that we have established the mathematical foundation and the properties of logarithms, let's walk through the actual process of applying them. When you encounter a function, y equals f of x, that consists of a complex combination of products and quotients, you can avoid the cumbersome product and quotient rules by following these 5 steps. Step 1 is to take the natural logarithm of both sides of the equation. Instead of working with the function as it is, we rewrite it as log y equals log f of x. This simple step allows us to use the properties we just discussed. Step 2 is to expand the expression. Here, you will apply the product, quotient, and power rules of logarithms to break down the log of f of x. The goal here is to transform a complicated single term into a series of much simpler additions and subtractions. Step 3 is to differentiate both sides implicitly with respect to x. Now, this is a critical part of the process. On the left side, the derivative of log y with respect to x is always 1 over y, multiplied by di over dx, which is a result of the chain rule. On the right side, you simply differentiate each of the simplified terms you created in the previous step. Step 4 is to isolate the derivative. Since our ultimate goal is to find the value of di over dx, we need to move the 1 over y term. We do this by multiplying both sides of the equation by y. This results in di over dx equaling y multiplied by the derivative of log f of x. Finally, step 5 is the final substitution. To ensure your final answer is expressed solely in terms of x, you must replace the variable y with the original function, f of x. Once you have mastered this sequence, you'll find that even the most intimidating functions become quite manageable. Let's move on to the next slide, where we will apply these steps to a worked example. Worked example. Now that we have discussed the theoretical foundation and the step-by-step procedure, let us apply these concepts to a practical example. Please look at the problem on the slide. We are asked to differentiate a function where y equals the quantity x plus 1 cubed, multiplied by the quantity x minus 2 squared, all divided by the quantity x plus 3 to the power of 4, multiplied by the square root of x plus 4. Looking at this expression, you can see that using the standard quotient or product rules would be incredibly tedious. This is exactly where logarithmic differentiation becomes our most efficient tool. Let us begin with step 1. Take the natural logarithm of both sides. By doing this, we rewrite the equation as the natural log of y equals the natural log of the entire fraction we just described. Now we move to step 2. Expand the expression using the logarithmic properties we covered in the previous slide. First, we apply the quotient rule, which allows us to split the fraction into a subtraction. This gives us the natural log of the numerator minus the natural log of the denominator. Specifically, the natural log of the quantity x plus 1 cubed times x minus 2 squared, minus the natural log of the quantity x plus 3 to the power of 4 times the square root of x plus 4. Next, we use the product and power rules to break these down further. For the first part, the exponents 3 and 2 move to the front, giving us 3 times the natural log of x plus 1, plus 2 times the natural log of x minus 2. For the second part, we must be careful with the subtraction sign. We expand the denominator as 4 times the natural log of x plus 3, plus 1/2 the natural log of x plus 4, remembering that a square root is the same as a power of 1/2. When we distribute the negative sign across the denominator's terms, our fully expanded expression is the natural log of y equals 3 times the natural log of x plus 1, plus 2 times the natural log of x minus 2, minus 4 times the natural log of x plus 3, minus 1/2 the natural log of x plus 4. Now we proceed to step 3. Differentiate both sides with respect to x on the left side. Applying the chain rule, the derivative of the natural log of y is 1 over y. Multiplied by the derivative of y with respect to x on the right side, we differentiate each term individually. Since the derivative of the natural log of a linear function is simply 1 over that function, we get 3 over x plus 1 plus 2 over x minus 2 minus 4 over x plus 3 minus 1/2 over x plus 4. Step 4 is to isolate the derivative. To solve for the derivative of y with respect to x, we multiply the entire right side by y. This gives us the derivative of y with respect to x equals y, multiplied by the sum of those 4 fractions we just calculated. Finally, step 5, final substitution. Since our original problem was defined in terms of x, our final answer should be as well. We replace y with the original complex fraction. The final result is the original function, the quantity x plus 1 cubed times x minus 2 squared, divided by x plus 3 to the power of 4 times the square root of x plus 4, all multiplied by the bracket containing 3 over x plus 1, plus 2 over x minus 2, minus 4 over x plus 3, minus 1 over 2 times the quantity x plus 4. As we move forward, keep this process in mind, as there are a few common pitfalls in these steps that we will discuss in the next section. Real-world application context. Now that we have walked through the step-by-step mechanics of the process with a concrete example, let us examine why this technique is so valuable in practical, real-world applications. In professional fields such as economics or biology, scientists frequently encounter a concept known as relative growth rates. To give you a better idea of how this works, consider a population growth index. This index is often determined by a ratio of several competing factors. For instance, the available food supply, the amount of physical space, and the level of predation. Because these variables interact in complex ways, the resulting mathematical formula is typically a complex quotient of powers, very similar to the expression we just differentiated in the previous slide. Now, if a researcher were to apply the standard quotient rule to such a function, they would be faced with a massive and unmanageable algebraic expression, which significantly increases the likelihood of making a mistake. This is precisely why economists and biologists choose to take the natural logarithm of the index instead. By applying the logarithmic properties we discussed earlier, they transform a multiplicative relationship into an additive one. This is a powerful shift, as it allows them to observe how a percentage change in one specific factor, such as the food supply, contributes linearly to the overall growth rate, making the analysis far more intuitive and streamlined. Common mistakes to avoid. Now that we have walked through the step-by-step procedure and a detailed worked example, it is crucial to discuss some common pitfalls to ensure you avoid these mistakes in your own calculations. First, let's address a conceptual error regarding the logarithm of a sum. A very common mistake is assuming that the log of a plus b is equal to the log of a plus the log of b. Please be aware that this is completely incorrect. As we discussed in our foundation slide, logarithms are designed to split products into sums, but they cannot split a sum into separate logarithmic terms. Secondly, pay close attention to the final algebraic steps. When we differentiate the left side of our equation, we obtain 1 over y times di over dx. Many students correctly perform this step, but then forget to multiply the final result by y to isolate the derivative. Always remember that the final derivative, di over dx, is equal to y multiplied by the derivative of the expanded logarithmic expression. Finally, be vigilant about sign errors during the expansion process. When you are expanding the logarithm of a quotient, such as a divided by b, you subtract the log of the denominator. However, if the denominator consists of a product, such as b times c, you must remember that every term in the denominator must be subtracted. Therefore, the log of a divided by the product of b and c is written as the log of a minus the log of b minus the log of c. By keeping these 3 warnings in mind, you will be much more likely to reach the correct solution consistently. Key takeaways. To wrap up our lesson, let's go over the key takeaways to ensure you have a solid grasp of this technique. First, let's talk about efficiency. As we discussed at the beginning of the presentation, while the standard product and quotient rules are useful, logarithmic differentiation is the preferred method whenever you encounter a function with more than 2 factors or complex powers, as it prevents the algebra from becoming unmanageable. Secondly, remember the core goal of the transformation process. By applying the properties we studied in the second slide, we are essentially converting multiplication into addition, division into subtraction, and powers into simple coefficients. This simplification is what allows us to differentiate the expression term by term. Third, keep in mind the importance of the chain rule. The entire process relies heavily on the implicit differentiation of the natural log of y, which, as you saw in our step-by-step procedure, always yields 1 over y times the derivative of y with respect to x. Finally, and most importantly, referring back to the common mistakes we just covered, always remember the final step. To get your final answer, the derivative of the expanded expression must be multiplied by the original function y. Without this step, your solution remains incomplete.